Okay, thanks. Now, we'll just go through this. I hope it works. I've never actually done this before, so I'm now sharing the screen. I see the presentation I want to give, and if I get it right, when I click on that and that.
Perfect.
Now, what are we getting? We should be getting quite a bit of extra junk in there, no doubt. Can you see this horrible Zoom screen, or is that blocked out?
That was blocked out, but now you've clicked on it now. Yep, an unknown universe. We've got your header page, Alan, so you're right to go.
Okay, and you've got my talking head okay and everything else?
I have indeed.
Oh, good. What more could you ask for? Um, Very good. Well, as Reese said, it probably is going to work best for everybody. There will be two sections to the thing. I am going to take a 2-minute short break, very short break in the middle. You can grab a coffee or do whatever you need to do. Also, that each of those will be preceded by some question time. So that probably is going to work best. If there's anything you're absolutely bursting to say, then that's okay too. But okay, let's get going. And this is wonderful having Reese to do all the hard work of hosting a session. So off we go. Oh, just one final check. I'm now moving my mouse pointer about on the screen. Is that visible?
Yes, it is.
Excellent. Very good. So off we go. Now, welcome to everybody, and thank you very much for joining me this morning. I would feel very silly doing this talk if there was nobody out there. About a year ago, some of you, many of you actually, I noticed by your faces there, attended my session that was called Lifting the Lid On. In fact, there were 6 sessions, and I talked about space, time, gravity, chance, and a whole load of other things. And a couple or two or three of the things I'm going to touch on today were in those 6 talks. However, we're going to be looking at them in a totally different way. Then I was interested only really in what space, time, gravity, etc. was. Today, I'm much more interested in how we found out about those things, and in particular, what we don't know about those things. You see, we humans, we think we know a hell of a lot. Homo sapiens, the knowing humans, have been around for well over 200,000 years. Many would say 250,000 years ago was when we first evolved. And yet that's really, on this planet, only a very short time. The Earth was born about 5,000 million, 5 billion if you a bit of Americanized, years ago. And from now, there's a long way. But you know, we didn't even crawl out of the sea until the last 10% of that journey from birth to now. Imagine, for example, that the whole from the Earth's birth to now is like a trip, the road trip that probably many of you have done from, say, Burnie to Table Cape, roughly 20 kilometers. Imagine that, making that road trip. Of course, the start of the universe would have been back in Devonport if we'd been making that trip, about 3 times as far. But there we are. Okay, let's imagine that journey. The earliest humans of any sort, not Homo sapiens, but Homo stand-uppers. Now, I always call it that. The real name you probably know is Homo erectus, but that's a bit rough, probably. I might get into trouble streaming on the internet. The porn police might be after me for that. So let's call it Homo stand-uppers. Homo stand-uppers came along 2 million years ago. And they already had shelters, they knew about tools, they knew about hunting, they even had some simple medicines. But in our journey from Burnie to the Table Cape Lighthouse, we're already standing on the lighthouse steps when Homo stand-uppers comes along. And if we're talking about Homo sapiens, then we were just we're touchable on the lighthouse itself, or even the center of the lighthouse, because we're less than an arm's length away. That's how recent we are on this planet. It's not very long, and yet we've achieved one heck of a lot. You see, if we go back even 2,000 years ago, which is not very much at all, we had strongly developed societies, we had sophisticated buildings, we'd already measured the size of the Earth, and I'll be touching on that in a few minutes. 100 years ago, many of us, not all, had quite comfortable dwellings. We knew about science, quite a lot about science, and we'd already traveled by land, sea, and we were going into the air. And now, of course, we understand many, many more things, such as what the sun and the stars are, the power sources, nuclear energy, also space. We've been into space, and we know our place in the universe. So in part one of this talk, let's say, what is our place in the universe? And more importantly this time, how did we get to find out? Now, we all live on the South Island of Australia. The South Island, of course, there is other islands, but they're not very important, so we won't worry too much about those. So we live on the northwest coast of the South Island of Australia. Australia itself, of course, is on the top of the world, and so it should be, and Tasmania's even on the top of Australia when we put a proper map. Remembering, of course, in astronomy, there's no up or down as such. It's only conventions. We live, of course, on planet Earth, and Earth is just one of many planets. We have one moon, which is considerably smaller than the Earth. That is the Earth and moon to scale, as I've shown in previous talks. And it's good to do because you'll never see it in a book. It wastes too much space. But those are the moon and Earth to the real sizes and real distances. Of course, the Earth is only one of several planets. Those planets all orbit around the sun. And this is hopelessly not to scale, either in size or distance. There's huge distances between the planets. And as regards the scale of the sizes, there's the Earth, that tiny little speck down there, compared with the size of the sun. The stars, of course, are other suns, many, many, many of them much bigger than our sun, and some smaller too. You see, if the sun were the size just of an orange, like this, then to go to the next star would be about 2,000 kilometers away to the same scale. Let's say roughly Brisbane as the crow flies. So the stars are separated by a huge amount of distance. Also, of course, our sun is in what's being called the unfashionable outer suburbs of our galaxy. Way, way out, in no important place at all. And that, our galaxy itself, is just one amongst billions of other galaxies, all in a universe which is stretching and has been for 14 billion years, 14,000 million years. Let's take a 1-minute history trip of the whole universe, not in space, but in time. Our universe was made 14 billion years ago, as I said, out of absolutely nothing. Nothing at all. But out of nothing came everything. All the things we see around us, of course, but all of time and space. The universe wasn't created in any particular place because there were no places for it to be created in. Space itself was invented at that time. That moment of creation has been called rather facetiously the Big Bang, which suggests it was some sort of an explosion. In fact, it wasn't, as I mentioned last year in my talk on the universe. But never mind about that for the moment. Everything was born 14 billion years ago. And before that, there can be nothing. Then, just a tiny fraction of a second later, the universe, we believe, grew incredibly bigger. You can see all the numbers up there, all those zeros up there, in that amount of time, an incredibly tiny fraction of a second. We call it the inflation event, and we think it happened, though we're not absolutely sure about that. A little bit later, after that, for another few million years or so, there was a slow expansion of the universe, during which the atoms, galaxies, and then the first stars all formed. And then 10 billion years ago, it started to accelerate. And we've no idea what caused that. We've got a good name for it. We call it dark energy. But in fact, we've no idea what actually caused it. So we Homo sapiens have indeed, in our time, discovered a lot about the universe. Though many would say the most significant thing of all, of course, is just how insignificant we are in it. In fact, the history of the universe is really a sense of demoting ourselves from an important position, at least in the physical sense. And of course, it's a history of how much we don't yet know. Let's just talk about knowing for a minute. You can do it different ways, and I'm not a philosopher, but in fact, knowing and awareness are slightly different, and this will be important for the rest of this talk. It's possible to know something and also be aware that you do know it. For example, if you have some sort of talents, perhaps in drawing, for example, you may have done quite a few drawings and people say, yeah, they're not bad, very good. So you know something and you're aware of it. It is possible, though we're not going to be touching on this very much in this talk, to know something but not be aware. In other words, you may be a good drawer, but you've never tried it. So in fact, you're unaware that you do have that talent. Down here, though, you may well have tried drawing and you find you're lousy at it. In other words, we are not able to do something, we don't know about something, but at least we're aware that we don't know. And that is a bit of knowledge. And finally, of course, it's possible that you've never tried drawing, you don't know anything about it, you don't know whether you're good or bad at it, and you certainly can't do it. So we don't know, and we don't even suspect things. These colored boxes, green, blue, and red, are what I'm going to be touching on very shortly. In fact, that leads us to 3 questions, which is about the rest of this talk. And that is, what do we know that we know? That is the information we have and we're pretty confident of, and how did we find out? Nextly, what do we know that we don't know? And what are we doing about it? And the third one is, what don't we know that we don't know? And how can we find out things that we don't even suspect? All of those are questions I'll be asking about our universe. Just before we leave this philosophy bit, the way I like to think of it is what we know is like the land here, the colored land. What we know that we don't know is like an inland lake. Hopefully the land will encroach upon that lake over time. And what we don't know that we don't know is like a sea, which is outside that land. And we don't know quite how big that sea is. If we wanted to put that other bit in, things that we really do know, but we don't know we know, you might regard them as a little island that at some point we hope to connect, as it were, to the mainland. Of course, the horrible suspicion is that it's much more like this. This is what we really know, and there are so much more that we don't know. So to start with, let's look back at what we've already found out about our universe. And much more importantly for this talk, how did we find it out? So that brings us to part 2. What do we know we know? How did we get to know? And what can it teach us for the future? The very first astronomers, at least that we know of, were almost certainly Australia's first peoples. They predate Babylonians, Chinese, Mayas, Egyptians, all the rest of them, by tens of thousands of years, at least 60,000 years. And now there is a suspicion, talking to some of my historical colleagues, that in fact it could be approaching 100,000 years for the first peoples in Australia. You see, Australia's first peoples weren't particularly interested in what the stars and planets were in the scientific sense that we now consider. But they were very interested in how the heavens could be used for purely practical purposes and to reinforce moral, ethical standards. You see, in this picture, the sky looks as though it's sort of connected to the land. The sky wasn't remote to these people. It was a connected part of the land and the people. It was just there. It was roughly as close as the land was. And when they looked up in the sky at the Milky Way, for example, spanning several of our present constellations, though, there was the great emu, the idea of a bird in full flight. That bird was running, but only at certain times of the year. When the great emu was running, many tribes knew that that was the correct time to hunt it, as sustainable hunting. On the other hand, at different times of year, that emu looked as though it was lying down, or at least sitting on its eggs. And that was the time you could sustainably collect its eggs. Coming much closer to home, of course, 5,000 years ago in 3000 BC, we have Stonehenge. It didn't look like this originally in Wiltshire, England. And the important thing about Stonehenge is actually not the stones, but a series of 56 holes that we call Aubrey holes. They're named after the archaeologists who first realized their significance. They have burial remains underneath. Much more importantly, though, they can be used to predict eclipses, and I can tell you why on another occasion. Coming closer still to home, Egyptian astronomy was used for determining the dates of religious festivals, the hours and days. Why we have 12 hours in the day and 12 hours in the night comes from the Egyptians. More importantly, of course, they were very interested because the rising of Sirius together with the sun, what's called the helical rising, if you want a very posh word, indicated the flooding of the Nile. And that was an important point in the calendar year. Chinese astronomy, well, they were well up in star maps. They'd mapped the heavens very well, and they also could predict eclipses very, very accurately indeed. So what can we learn from this? Understanding how the heavens work requires careful observation, but it can be used for all sorts of everyday aspects of human life. By the time we get to ancient astronomy, though, that is a few hundred years BC, things are well underway astronomically. Anaxagoras, the philosopher, said, the purpose of life is the investigation of the sun, the moon, and the heavens. Anaxagoras also realized that the sun and moon were just large other bodies. He called them gigantic spherical rocks. Not bad in the case of the moon, but not quite right in the case of the sun. With the moon reflecting the sun's light, that's a very good explanation for the moon's changing shape, as I've talked about in previous talks. The philosopher Seleucus said the tides are caused by the pull of the moon. Quite right, we know that. But their height also depends on the sun's position. That's something that people nowadays often don't realize. That's the reason, of course, why we have king tides and lower tides, neap tides. It is because the sun and moon are pulling together rather than apart at different times. Plato, the famous philosopher, said astronomy compels the soul to look upwards and leads us from this world to the next. He was particularly interested in promoting the harmony of the Earth, Sun, Moon, and planets. And it was largely his influence, together with Pythagoras, that had the idea that the harmony of the heavens, the harmony of people, and the harmony of mathematics were all somehow connected. And he was quite right. In fact, geometry, which of course the Greeks developed, allowed them the first accurate measure of the size of the Earth. At a certain time of year, the sun could shine right down a deep well in Syene. And when it did, you knew the sun was overhead. On the other hand, at a certain distance away, a column in Alexandria, for example, would be casting a shadow. And by measuring these angles, by measuring the sizes, and also, by the way, measuring the distance between these two places, and Eratosthenes actually employed professional walkers that were very good at walking at the same speed with the same strides all the time to measure that distance. When he did, with a little bit of geometry, you can get the size of the Earth. And they weren't out by much. They got it right within 10%. Aristarchus went on to measure the distance to the moon. This is fairly tricky, but the Earth casts a shadow which the moon enters during the course of an eclipse. He was able to work out with his geometry what the size of this shadow would be. And he also knew, of course, that the moon went round the Earth in a certain time. He also knew how long it took for the eclipse to happen. And by taking all those ratios, a good bit of mathematics, he was able to figure out exactly how far away the moon was. They also got the distance to the moon by a different method. If you're on two different places on the Earth, say here, this is grossly exaggerated from what they were able to do, but from A, the moon appears against distant stars here. On the other hand, from B, it appears against distant stars up here. And by measuring that different an angle where the moon was, parallax it's called, you could actually figure out the moon's distance. What can we learn from that? Well, mathematics is a very important tool for understanding our universe. By the time we get to the 1600s, what's been often called the scientific renaissance, then we are on to people like Johannes Kepler, the German. He made very detailed observations of how the planets move in the heaven and the speeds and times that they actually do that moving. And from that, he was able to work out how the planets move around the sun, which of course was then the received wisdom. He found the planets move around the sun in a very special sort of squash circle we call ellipses nowadays. A lot of people call them ovals, but I suppose technically an oval is an egg shape from over. However, these are special sorts of squash circles that we call ellipses. Furthermore, when the planet was nearer to the sun, it moved quicker. On the other hand, when it was further, it moved slower. On the other hand, it also, how many hands can you have? It also carved out the same area in equal times. That was a very, very clever deduction just from seeing motions in the sky. Finally, he figured out the third law, that if you took the year of a planet, that is how long it takes to go round the sun, then the square of that year as a number is proportional to the cube of its distance from the sun. And that allowed the relative distances of the planets from the sun to be calculated. We learn from that, of course, that painstaking, long-term collection of data is very often very useful in figuring out how the universe works. Using Kepler's laws, Isaac Newton, of course, was to go on to work out what the law of gravity was. Of course, he wasn't interested in apples. He knew full well that gravity itself actually caused apples to fall down to the earth. He was very interested, though, in why the moon didn't fall down and hit the earth. The answer, of course, is it's moving around it too. But the speed at which it moves around could be deduced from Kepler's laws now with a bit of complex mathematics. So complex, in fact, that Newton had to invent a whole new branch of mathematics. Many would say possibly the most important branch of mathematics there is, what we call nowadays the differential and integral calculus. Forget that, but it was a whole new branch of mathematics. And like many discoveries in science, it was co-invented at the same time by Leibniz in Germany. However, the important bit was he figured out exactly how bodies attract each other. The fact that the square of the distance, as the distance increases, the force drops off as the square of the distance. Also, that in fact, the force of attraction is proportional to the product of the masses, the amount of stuff in the two bodies. Very, very important laws for the future. And we can certainly learn from that, that sometimes to get on with your own problem, you need an advance elsewhere. Now, of course, by the 1600s, Copernicus, Kepler, Newton, they knew that we had a universe that was centered on the sun. And by the 1600s too, they also knew that the other stars in the sky were almost certainly other suns, much fainter, of course, and therefore almost certainly much, much further away. And that led to the question, how big is this universe? When had it all started? You see, if you'd asked Isaac Newton, Isaac, you know, how big is this universe? He would say it would go on forever. It was infinite in size, with infinite numbers of stars stretching out forever. He would have also said it was infinite in time. Very easy concept, but very mind-boggling too. It had always been there and always would be there. But this raised several problems. The only one I'm going to touch on, though, is what's been called the dark sky problem. Why was the sky dark at night? You may say, well, just because the sun's not there. No, what we're talking about here has often been called Olbers' paradox, from a guy in the late 1700s who made it very popular. However, Kepler knew about this problem, and Newton certainly knew about this problem very well. What's the problem? Let's have a look at it. Imagine you're here on Earth and you're looking out into space at different stars. Well, there's lots of dark space between the stars, here at least, though some lines of sight hit a star. On the other hand, if we put a bit more of the universe in, then more of our lines of sight hit a star. However, there are still plenty of gaps. So let's put more stars in. As you put more stars in, more and more of your angle, more and more of your line of sight hit a star, and there's less and less dark sky behind those stars. Let's look at it another way. If you're in a forest and the forest truly goes on forever, it doesn't matter how sparse those trees are planted. All you can see in the distance is wood. And that meant that when we look up in the sky, the whole of the sky should be as bright as the surface as any star if it truly went on forever, just like that. But of course, the sky wasn't enormously bright. So did this mean that the universe stopped somewhere? It was limited in size. It had an edge. Well, no, it was going to be a heck of a long time, though, before anyone was to work that truth out. But what can we learn from that? The answer is sometimes the very simplest of questions, the very simplest of observations can lead to very, very important discoveries. Oh, and yes, sometimes you have to have a lot of patience before a problem gets solved. Let's move on, though, to what's often been called the Age of Enlightenment, the 1700s onwards up to the late 1800s anyway. By then, the distance of the planets relative to the Earth's was well known. Take the Earth as 1 or perhaps 100%. We knew that Venus, this comes from Kepler's laws, that Venus was 70% of that distance, Mercury was 40%, Jupiter was 500%, 5 times as far from the Sun as the Earth. But no one knew what the scale was. We didn't know. If we could just measure any one of those distances accurately, then we would have the scale for the whole of our solar system. In particular, we'd know the distance of the Earth from the Sun, or Jupiter from the Sun, or Venus from the Earth. One distance would provide the answer to everything. This, of course, leads us to the famous transit of Venus of 1769. Now, we astronomers take a slightly different view of this than does a lot of historians. This, of course, is Jimmy Cook's first voyage, 1768. I refuse to call him Captain Cook. He wasn't a captain on that trip. He was indeed the master of the ship, but he was a lieutenant. And in 1768, he set off on HMS Endeavour, ostensibly to actually observe the transit of Venus. Of course, we all knew the real reason was his secret orders, which in fact was to discover the Great Southland. But that's another story for another person, for another day. What was known at that time, by precisely measuring how Venus transited across the Sun, which is a very rare event, by the way. You do get 2 8 years apart, but then you don't get any more for over 100 years. So that's just the way things are. However, by accurately measuring the times of these contacts, as they're called, when the Venus first touches, when it's fully inside, and then when it comes out of the Sun during a transit, it was realized that the distance from the Earth, Venus from the Earth, could be calculated, essentially by a parallax method. So the Royal Society of London commissioned an expedition to Tahiti, and it was funded by the King. It was also going to be observed, and we often forget this, from Hudson's Bay in Canada, and also from Nordkapp in Norway. However, the important measurements, or probably the most important, not the only important ones, were going to be made from down here in the south, because they were a bigger distance apart. Although this looks a massive distance, of course, it's not really that far apart. So that was the way it was set up to be made. Now, unfortunately here, the astronomer on board was Charles Green. Jimmy Cook, of course, also had Joseph Banks, the botanist, on board. And Cook insisted that the important observations on Tahiti, which is where they were going to be made essentially by himself, Cook, and by Banks. In other words, a captain of a ship or a master of a ship and a botanist. And Charles Green was not going to be taken very seriously at all. He was a fairly young man. Unfortunately, Green was well aware of a very difficult problem of what's called the black drop effect, that in fact it's very difficult to measure a black object against a very bright surface. So the drawings that Cook made, in the end, turned out to be rubbish. And Charles Green's drawings were much more accurate. It's a wonderful story for another day, which I'd love to tell you, the full story. However, when Cook sent his and Banks's drawings in, and also Green's, though he said these are not much cop, they're very different, the society blamed, they were very disappointed in the data as a whole, but they and Cook blamed the astronomer Charles Green. But in fact, Green's drawings were much, much better than Cook's and Banks. In fact, Green died of shame on the way back to England. So had no chance to present his own data, nor defend himself. A very sad story, but what can we learn from it? Well, leave it to the professionals, please, not just the willing or even gifted amateurs. But now let's turn our attention to telescopes. Of course, for many thousands of years, people only knew what they could see with their naked eyes. But Galileo's telescopes that came along in the 1600s changed all that, in particular by revealing that Jupiter had moons. They went round regularly. They basically obeyed the laws of gravity, though he wasn't going to put it that way for a few years. But that started 400 years of telescope building, which has caused an unbelievable revolution in how we understand the universe. You see, astronomers use telescopes to reveal what our naked eyes are unable to see, either because things are far too faint, and telescopes collect a much more light than the little quarter of an inch, few millimeters that our eyeball is, or things they can see much more detail. Again, that's caused by the fact that our eyes are very small. Galileo, in a famous picture, is seen showing his new telescope to the Doge, the governor of Venice, in 1610. A little bit later, Johannes Hevelius, the Polish astronomer, had built a massive telescope. It was very long, only had 2 lenses, but must have taken a whole army of people to move it around. But with them, new discoveries really started pouring in. Also, another telescope was Isaac Newton. He was the first one to build a reflecting telescope that uses a mirror rather than a lens. And that's the basis for essentially all modern telescopes, rather than the Galileo style of telescope. William Herschel in 1788 went on, he was the essentially German/English astronomer, went on to build a massive instrument. And of course, a few years earlier, he'd already discovered a new planet with a smaller telescope, the planet Uranus, by seeing that it moved against the background of stars. So he was really fired up. What we often forget, though, is that William was hugely assisted by his colleague and sister, Caroline Herschel. They mapped our local system of stars with these new telescopes, and they found that the stars were not just random throughout the universe, as they would have said, but in fact were all clumped together. This was the beginning of a suggestion of what we would later be calling galaxies. Caroline Herschel is well worthy of looking up, by the way. The book by Marilyn Ogilvie, Searching the Stars, is a lot of fun. And she, that is Caroline Herschel, was the first woman to be awarded the Royal Society, London Royal Society's gold medal, a stunning colleague to William. With these new telescopes, they allowed measurements of the distances to the nearest stars. The stars, the nearest stars at least, are far too far away to use the parallax method, excuse me, of determining distance. But there is a very clever method. If you wait 6 months, the Earth is in a very different place. You need a long baseline to look out into space. So, for example, in January, this near star appears against the background of these distant stars over here, as seen here. On the other hand, in July, this same star appears to have moved against the background of stars there. By actually measuring the angle that it appears to have moved, you can easily work out by very simple geometry the distance to these stars. These telescopes were necessary to do that, though. So what can we learn? Well, one of the biggest things we learn in astronomy is that new instruments, new methods of looking at the universe, almost invariably lead to major discoveries. Now, at this point, I'd like to just pause in our thoughts for a minute. This isn't one of the question times, so that will become very shortly, though. At 1900, as we came up to 1900, there was a lot of people arguing that everything about the universe had been discovered. In fact, they were arguing that everything in science had really been discovered. We knew where we lived in the universe. Copernicus had argued successfully that we're in a sun-centered universe. Newton had his laws of motion. We had modern chemistry. We've got the laws of motion of the planets. We've discovered Jupiter. We could go on, Neptune. We could go on forever. Natural selection, germ theory, magnetism, and radioactivity, of course, was in its infancy. In fact, the famous quantum theory guy, Max Planck, was told by one of his teachers, von Jolly, don't go into physics. Almost everything else almost everything is already discovered. All that remains is just filling in a few unimportant holes. How wrong could he have been? The 20th century was to bring a total scientific awakening in astronomy, physics, in fact, all the sciences, but in particular in astronomy and physics. Galaxies, relativity, the expanding universe, you can read the list there. Quasars, pulsars, inflation, dark matter, dark energy, black holes, much, much more. So let's look at, before we take a break, at these final years. The modern era, I suppose, started really with the construction of the Mount Wilson telescope in California, a very, very important instrument indeed. At that time, there was an argument going on between Harlow Shapley and Heber Curtis, interesting names those, about what we now call galaxies. They were looking at things like this. The great debate of the 1920s was that Harlow Shapley said, look, these are other huge groups of stars. He called them island universes. We would now call them galaxies. On the other hand, Heber Curtis said, no, they're just bits of the Milky Way. And before you laugh at him, by the way, you should see the surroundings of this object. Is that a bit of the Milky Way? Or is it indeed something that's many, many, many times further? This indeed is a simulation, but it's an honest simulation. In fact, what we're looking at is the Andromeda Galaxy, available as it's seen in the best telescopes of the time. We now know it is a very distant galaxy. But the vital proof came from measuring how distant the stars in that object really were. That was the only way to measure its distance. And the key discovery came from a woman who was using those telescopes called Henrietta Leavitt, or was using the data that came from those telescopes. You see, the distances of the farther stars are too distant. The stars in that object are too distant to measure by the parallax method I just showed you. She had to invent a whole new method, and it's what I could call the brightness method. If you ask an astronomer, they will talk about a different name, but we'll come to that. But let's just pause for a second here and consider what brightness is. You see, the way an object appears depends on two things. One is how much power it's putting out, how bright it really is if you could get up close. And also its distance, because as you move something further away, it gets fainter and fainter. You see, for example, here we have two objects, the moon and one of the car's headlights, are looking sort of about the same in brightness. If anything, the truck's headlights looks a little bit brighter. But of course they're not. The moon is putting out a huge amount more light, or reflecting a huge amount more light than the truck's headlights. And that's because, of course, the moon is much further away. Now, Henrietta Leavitt's key discovery was that when she looked at a particular sort of star, an interesting star which didn't keep its same brightness, but pulsated, getting bigger and smaller, bigger and smaller. The time it took between getting bigger and smaller was related to how much power it was really putting out. In other words, what you would see if you were up close. And by plotting this up, it was called the Cepheid variable stars, period power relation, period luminosity relation, same word. That key discovery enabled us to know the brightness, the real brightness, if you were up close, of those stars. And it was easy enough to measure how apparently bright they were. From that, all you have to do is take the power of the stars and divide by the apparent brightness, and you get the distance, actually the square of the distance, but then you take a square root. It's pretty easy stuff once you've got the real power of a star. That discovery meant that many, many, many more stars could be measured, not just in our own galaxy, their distance is measured, not just in our own galaxy, but in distant galaxies. And that key breakthrough of Leavitt's led on to a series of astounding discoveries by Edwin Hubble. Edwin Hubble used those to show that these nebulae, these fuzzy things, this was an infinitely better picture, by the way, a modern picture than he would have been able to see, lay far outside our own galaxy. And that meant, this discovery, one, that there were billions more galaxies in the universe. What an incredible step forward. We suddenly realized that our universe was billions of times bigger, more massive than we'd ever suspected. The discovery too, though, was that all these galaxies are not just sitting there, but they're actually moving away from us. Not only have we realized that the universe had got bigger, the universe really was getting bigger all the time because it was stretching out, expanding away. They were moving in a very special way too, and that was the third discovery, such that if you looked at one that was twice as far, it was moving away twice as fast, 3 times as far, 3 times as fast. We call it speeds proportional to their distances. And that meant that all of space in the universe was stretching or expanding, as it was variously called. I prefer the word stretching because it's more honest, with the galaxies stuck in it. In a deep sense, the galaxies themselves were not moving. It was like sitting on a bus, perhaps. You may say, I'm sitting here, I'm not moving, but of course the bus itself is moving. In this case, space itself was stretching and still is, and has been for 14 billion years. This, of course, brings us to what's been called the Big Bang, facetiously called the Big Bang by its opponents, in fact. The original title was The Hypothesis of the Primeval Atom, in which George Gamow and the Jesuit priest, Georges Lemaitre, said, the universe was born in a single moment a long time ago, expanding from a tiny size. More importantly, by, as it were, winding the clock back, they were, in their minds, they could understand how long ago that was. We would now say it's 14 billion years. They hadn't quite got the numbers right at that time. We think we're doing much better now. But in fact, the universe was now born 14 billion years ago. The galaxies are getting farther apart. The universe is stretching out because space itself is expanding. We weren't going to get the proof of this, though, until 1965, when 2 guys working in the United States in New Jersey, Penzias and Wilson, realized that what they were seeing with their new telescope was in fact the faint glow of radio energy coming from everywhere in the sky, not just one point, one object. That was exactly as predicted by the Big Bang. It was also exactly of the right amount as predicted by the Big Bang. You could call it a glow from the beginning of time, because time itself was then created. What do we learn from that? Well, and obviously an apparently minor finding, like the Leavitt-Cepheid period luminosity relationship. We won't call it really minor finding, but it was supposedly a contained finding that only had small amounts of relevance, opened the door to momentous discoveries. You could say that Henrietta Leavitt, in one sense, was the godmother of our modern picture of the universe. So we've learnt a huge amount about our universe, we can say, in the last 100 years in particular. So perhaps we can now quite rightly boast that we know a hell of a lot about it, can't we? Oh yeah? And now it's time for perhaps a few questions. And then we'd like to take a couple of minute break. So Reese, if you'd like to open up, I'm very happy to try and answer whatever I can.
So would you like to stop sharing for a moment then, Alan, and we'll put everybody on the...
That would be good. I do that, and do I close that? No.
You should have a red stop sharing up the top.
Oh, yes, I clicked on the wrong one. Yep, good.
Okay, excellent. So everybody unmute themselves. If anybody's got a comment or a question, please go for it.
I've got a comment.
Sorry,
I've just got a comment, Veronica.
Sorry, who's speaking? There are so many people on the screen.
Veronica.
Veronica, thank you. Thanks, Veronica.
Alan, just to give you that whoever's speaking will be outlined in yellow. See how my...
Oh, yes, of course.
Okay, yeah. So go for it, Veronica.
I'm just having a lot of trouble keeping up because you say something and my mind goes right away with it in imagination and I have to rush forward and catch up with the next bit. So that's just my comment.
Okay, well, that's why we're making a recording, isn't it, Reese?
Yeah, so you can all go back and watch it. It should be on our website probably tomorrow.
Yeah, you can watch me for the rest of the week if you really are a big fan.
Anybody with a question? Yeah, Rob.
Thank you very much. It's a magnificent lecture that you're giving. It's a bit of a curly one. Is there a connection, and can mathematics describe it, between the morality, good and evil, and existence? As in, for example, evil could be depicted as 0 or nothing, and good, the absolute of good, could be depicted as light or something.
Wow. Okay, that is definitely a curly one. I'm not quite sure that you should be asking an astronomer scientist that question. It's definitely philosopher, possibly even theologian question. I think the theologians would argue for ages about what is good and evil and what is the personification of evil, literally, you know, whether Satan exists and so on. And I'm certainly not going to tread on anybody's toes there.
And is there an absolute of either of those?
Yes.
Look, honestly, I'm going to say, I don't know, which is what the rest of this talk is going to be about. You had the easy bit, the things we know, and after the break, of course, we will be getting to the don't knows. Please give me an easier one, somebody.
Jen, have you got a question?
Yes. You were saying that Henrietta Leavitt, you know, was to be accredited for the measuring the distance between stars due to the brightness of the stars. Am I correct?
Yes, well, particularly, yeah.
Yes.
The farther stars, and the ones in distant galaxies.
Yes. So that's assuming that the brightness is constant. Is that correct?
No, that was the point. The actual stars themselves vary between two levels of brightness. They go from a lower level to an upper level because the star itself is expanding and contracting. So although they vary, the time in which they vary there in brightness, that is the power, the amount of real energy they're putting out, is connected with how bright they are, and you can take your choice at the top or the bottom. Once we know one, we know the other, obviously. And therefore, from that, with the distance, the inverse square distance relationship, we get their real distance.
Right, because I was thinking with the flares and that on stars, that, you know, you'd have an brighter moments.
Yeah. That's a very clever observation. In fact, that's why she used this particular sort of star. There were stars that didn't have flares, and you can't just use any old stars for this job because most stars are fairly static in their brightness. But these particular Cepheid variables, by the way, that name comes from the brightest example of a Cepheid, which is in the constellation of Cephas the whale. And that's how astronomers tend to name these things. Cepheid variables do this in a very special way. Only these special stars, and actually a few more, are capable of doing it. I should say at this wonderful time, Hilary, who's been in her office, has just brought me a cup of coffee. So in a minute or two, thank you, Lynn. So you have to choose a particular star, and that's her brilliance, was finding this group of stars that you could do this job with.
Thank you.
Joe speaking.
Maureen, as I see, waving. Sorry, Alison.
Well, I will jump in because I'm going to have to leave for a doctor's appointment. And I'm so sorry about that, because it's brilliant. The way that you are explaining this is really good.
Oh, you're missing the best bit. You'll have to get the recording.
Yes, but I do want to ask you, will you be saying anything about if you have a telescope, what the best thing to do is?
No, that's not what this talk is all about. That's real astronomy. Perhaps at some point we could schedule that in if we're still in lockdown in a year's time. No, not a year's time, in a month or two's time. I could do that. A lot of that information is very good. And Martin George at the Launceston Planetarium is excellent on that. You can get that information freely. I'm happy to send you some of that, what's up in the sky and so on, if you want to. But the things to watch out for are Venus in the early morning sky, and Jupiter and Saturn, which are now getting further apart. I think I'm right in saying that. And they are visible as soon as it's dark enough at night.
Yeah, I guess I was thinking, I probably know that I can get stuff on the internet, but I'm just thinking about what magnifications and things like that, you know. But we'll talk another time.
Okay, well, look, let's talk about that. That's a good thing. We can talk about that at some point. Is there anything else related to what we know? I've done the easy bit so far.
I just had a comment. You mentioned two women who contributed significantly to what we know. And I guess my comment is a comment I'd make about science in general. They're women we've never heard of. Perhaps in the world of astronomy, they are better known, but everybody has heard of Hubble, but perhaps not of Henrietta. And
No, that is a very good point indeed. Funnily enough, in astronomy, women have been part. I could give a whole talk about women in astronomy. I have touched on them in other talks. Last year, I touched on several others. You could indeed talk about them. Probably there is no other science, with maybe the possible exception of the medical sciences, in which women have played a greater role. We've had women in astronomy. I mean, going back Caroline Herschel, or even before that, there were women have been making important discoveries. I mean, even fairly recently in my own lifetime, Vera Rubin, which you've probably never heard of, she's essentially the person who discovered dark matter, which I'll be talking about very shortly.
And that's exactly my point, Alan. You know, the significance of their contributions are essentially unknown to the general world, but the male stars, for want of a pun, are known to most of us.
Yeah, in fact, if you go into a modern telescope control room, I would say you would get very close to 50-50 women, men in modern astronomy. It's very close indeed. Yeah. Anybody else?
And historically, Alan, have these women's contributions been acknowledged equally to their male counterparts?
Oh, absolutely. I mean, Vera Rubin, for example, who died fairly recently, 10 years ago? Anyway, fairly recently. She has had a major observatory, the major observatory, many would say, named after her. In fact, they changed the name of the observatory to the Vera C. Rubin thing. Yeah, I mean, and they get, person I knew, well, she was way above me in age, and still with us, by the way, is Margaret Burbage. She was the founder, essentially, of the best information on quasars when they were discovered with radio telescopes. I worked with her, or rather the person I was working for in Australia when I first came to Australia was a very close connection with her. She was actually in America. John Bolton, my guy, was the Parkes Radio Telescope. He is responsible for that, which is another story for another day. Yeah, I mean, I met her, sat down with her, we've chatted and so on. She's still alive, aged 102, by the way, but she got stunning. She's had stunning acclaim. You know, she's been the president of the Royal Astronomical Society and a whole load of other things. What are we doing for time? Could I suggest that there will be one more opportunity for questions in a bit. I do need to take a 2-minute break. I've got a bit of a back problem. I need to stretch that back. I make it, what do you get? I've got about 10:56. Is that right, Reyes?
That's what I agree with. So, yep, shall we be back at...
Could we rejoin maybe 1 minute before 11 o'clock so we're all
Sounds like
down?
a plan. Okay, thanks, Alan.
Okay, I'm back.
Well, you're the important one, so that's good.
Okay, so I share again. And we share that. And so we should be back in business. Is that okay, Reese?
Yes, that's perfect.
Good. So do we have most people? What is it?
Yes,
Yep,
I think most people seem to be right.
Fine. So in part 3 of this talk, we're going to be talking about what do we know that we don't know? In other words, what is our knowledge of what our boundaries are? And of course, in particular, what are we doing about it? Isaac Newton famously said, what we know is a drop. What we don't know is an ocean. Let's just look at a few of them. We don't know why the universe exists, for example. Answer to that? Well, you better ask the theologians. That's not a scientific question. We don't know how you can create everything, time, space, matter, energy, out of absolutely nothing. Will we? No, probably never is my best guess. We don't know how many universes there are. Now, you'll probably read about this in the media. The media love parallel universes. The idea is that every time I scratch my head on one side, as opposed to the other side, I create a whole new universe. And every time you do something similar, just slightly different when there are two choices, or when quantum theory has two choices, suddenly we have a whole new universe. It's just absolutely ridiculous and mind-boggling. But that is the way that quantum physics, which is not at all much liked by astronomers, seems to be heading. Can this really happen? You better ask the philosophers about that one. We don't know why this thing called inflation occurred, and we don't even know if it really did, but it gets us out of a lot of trouble. I'll just spend a second or two on that one. You see, the idea is this: the universe is far too, when we look at the cosmic microwave background, and this is a map of it, that's that glow from the beginning of time I was talking about. When we look at that, it's far too uniform. It's as though you were perhaps a commercial traveler. You go to different parts of the world, and everywhere you go has got the same sort of decoration in your hotel room where you stay. You say, well, obviously it's the same chain, but it isn't the same chain. You say, well, okay, maybe they all have the same designer. Maybe there's only one supplier of these goods. But the answer is no, it's none of that. The universe is far too uniform for it not to have been in close contact once. And yet these places, as far as we're aware, have never been in contact unless you introduce this thing called inflation. We don't know why 80% of the stuff, the matter we call it, in the universe is hidden from us. We do have some possible ideas, and where we do have some possible ideas, I'll be mentioning. What I'm talking about here, of course, is dark matter, or sometimes called the missing mass, where most of the galaxies are spinning far too fast to hold themselves together. For example, let's have a look at it. Now, this is only illustrative, but the rotation we expect from the stuff we can see and Newton's law is here. It should be fairly slow. Of course, we don't actually see the galaxies spinning like this because the timescales are very long, but we can measure how fast they're spinning from observations of their stars. This is the rotation we actually observe, much, much faster. So what's the answer? Well, one is, and this is the dark matter answer, that there's much more stuff in there than we can see. And it's not just that we are not looking hard enough. Every technique we've used so far shows that we don't see anything. So in this case, though, dark matter is real. We've just got to go and find it. If so, what could it be? Well, various suggestions have been made. It could have been various sorts of failed or dead stars, stars that don't quite make it a star. It could be neutron stars, it could be black holes, and I've no time at all to go into what these actually are, though I have talked about them in previous talk. The problem is we've searched for all of these pretty damn carefully. We haven't found them yet, though the searches are still going on. What is the dark matter? Well, it could be other weirder stuff. Postulated hypothetical particles such as axions, don't ask, inert neutrinos, again don't ask, or weakly interacting massive particles, which is where the money is at the moment. But you know, they've not turned up yet. We don't even know if these sort of things exist. And in any case, much more importantly, they're not heavy enough to make up all the problem, the extra 80% of the matter in the universe. There's another possibility, though, and that is that we're using the wrong law of gravity to make these deductions. You see, that is the curve that we would expect for a rotation in galaxies. This is the curve we get. And if instead of using an inverse square law, I mean, and this is absolute sacrilege in physics, if instead of an inverse square law, you use what's called an inverse linear law, note there's no square power up here, you get a much better fit to what's called the rotation curves of galaxies. But wow, that is a revolutionary idea. Moving on. We don't know why the universe is accelerating now. Like people often do when they have a problem, they stick a stamp on it, a name, and that's all we've got. We call it dark energy. We have some very vague ideas, but to be honest, none of them really work. We don't understand how the universe will end. That's testable. We can make measurements. Perhaps works in progress. We could actually come to some conclusions, but it's some time off yet, I think. We don't understand time. Now, a year ago, I gave a whole talk on time, and much more recently, of course, we had a very good U3A talk on time. And neither of us, of course, understood it. And yet we use it all the time. Some of the questions really are philosophical questions, I think. And yet time is part of just about every basic equation in astronomy. Time, they say, flows like a river. That is, we're standing on a bank and we're watching things appear and flow by us. But if time really is flowing, what is it flowing relative to? I mean, a river flows against its banks. But what is time flowing to? Well, it can only be another time, and that's just pushing the thing back. Maybe that's why it's a philosophic question. Of course, we have time travel. Everyone's very keen on that, or keen on hearing about it. Possibly the most mysterious thing of all. Why is it that we can move up and down, side to side, forward and back so easily in space, but we can't move at all in time? Not even 1 second. Sometimes when I've said something that I really wish I hadn't, I wish I could go back a minute or two, but you can't move in time. Why? We don't know. If you could, of course, then you could do things in a different order. You could, for example, retire and then start school. Some might like that, some might not. You could go and start work and then be born. And in any order, you could visit, say, these events of your life. And that's just so ridiculous that we laugh out loud. But why? Why can't we move in time? Time and space, we now know from the theories of relativity, are fairly accurately, fairly deeply coherent together. We also don't know why our universe is so lopsided, all matter and almost no antimatter. We're baffled at the moment. Let me explain. The modern theories of particle physics, the things that our physics, we astronomers, our physics colleagues say, is that for every particle, there is an antiparticle. The electron has an antiparticle called a proton. From the protons is an antiproton. And these things are being created in space all the time. Certainly at the beginning of the universe, then matter and antimatter should have been made in exactly equal amounts. But when we look around us, there's only one sort of stuff, what we call matter. Where's the other stuff? We don't understand how gravity works. And this is the holy grail of physics. Gravity is probably the most common force in our everyday lives. We know of 4 forces in nature. We'll call them the strong nuclear force, the electromagnetic force, the weak nuclear force, and gravity. And we have a pretty damn good idea of the first 3 forces. They fit nicely into our quantum world, but gravity doesn't. And according to quantum physics, we have virtual particles. A particle pops up here and an antiparticle pops up somewhere else in the universe, possibly across the other side of the universe. And then they destroy each other. We have these entangled particles. Whatever one does, the other has to do the opposite immediately, not after a delay, but immediately. Immediately, even if they are on the opposite sides of the universe, billions of light years apart. And that, of course, flatly contradicts Einstein's theories of relativity, in particular the general theory, which is a theory of gravity. So we're certainly missing something big in tying gravity into everything else we know about physics. We are really missing something big. That's why I call it the Holy Grail. Of course, we don't know if there's any life on other worlds, or are we alone? I have talked about this fairly extensively, at least twice in U3A, and we can ask a question or two. I believe we will have the answer to that one now within about 10 years. We will know that we are not alone. However, people might disagree, and it's all right to disagree with me if you like. I mean, I can't force you to be right. So how sure am I that we're going to find some of these answers? Well, we've been asking for quite a long time. Where did it all come from? Well, sorry, I don't know. I don't know where the answers are going to come from. All I know is that people are working hard. But then, as Asimov famously said, people who think they know everything are a great annoyance to those of us who actually do. And therefore, it gives me an excuse for not knowing quite everything. So now we're talking about discovery, the getting of wisdom, the getting of knowledge. In the final part, quite short part of this talk, I'll be saying, well, what don't we know that we don't know? And how can we discover things that we don't even suspect yet? How can you get answers when you don't even know the questions to ask? And how can I possibly be giving a talk about what I don't know? Well, it's never stopped me before, so I'll carry on if you don't mind. But here we go. How do you make scientific discoveries? Let's quickly review some of those lessons that I mentioned in the first part of the talk. Mathematics is essential. It's the language of science. It's essential for understanding the universe. You need careful collection of data if you're going to figure out how the universe really works. And very often you need a breakthrough in a different area of knowledge to solve your own problem. Sometimes very simple discoveries can lead to much more important ones. New instruments are invariably important. And I'll just stop on this one for a second because it is so important. Oh, perhaps we better carry on. Also, I think I've already had that. Oh, I'm going backwards. I seem to be in a bit of a tiz-was here. Let's move on. So let's ask again, how do you make scientific discoveries? How is modern science actually done? There seems to be 3 ways that work for us. One you could call serendipity, a good word in U3AW, I know. That's simply watching carefully for things to turn up. The other is discussion and argument. Thirdly, building new instruments. Isaac Asimov, that same guy, said the most exciting thing to hear in science is, that's funny. Watching, waiting, and then following up when something new, surprising turns up. Another one is discussion, argument, because differences of opinion are not bad in science. They're useful. It's not just egos, though there's some of that in it too, but differences of opinion are useful in flushing out what's good and what isn't. Constructive argument, let us call it, is vital in pinpointing what we don't yet know. New instruments are, well, seeing further and better, opening new parts of the spectrum up, are very important indeed. I'll just do a little aside. This is the aside I was going to mention a second ago. I was connected really with 3 new projects. One, I had nothing much, I didn't have anything at all to do with the building of the Parkes Radio Telescope, though I spent a heck of a lot of time there as the principal astronomer in my latter part of my career. But I did talk extensively with the people who were responsible for building that brand new, by Australian standards, very expensive instrument. I was much more closely attached to the people who were building the Anglo-Australian telescope because they were my contemporaries. And I was also someone who used that fairly extensively. And finally, the new radio telescope up at Narrabri that worked together with the Parkes Radio Telescope, called the Compact Array, forming the Australia Telescope. I was one of the lobby group that was pushing the politicians to actually get those built. Now, I don't say any of that to sort of be immodest or anything. The lesson we learned, though, was that for each of these instruments, talking to people or actually seeing it at first hand, the politicians, the funding groups said to us, tell us what you're going to learn. We must know before we give you all that money, what you're going to learn from that. And in the early days, they didn't do that. In the later days, we'd learned. We made extensive lists of what we were going to find out about the universe from these new instruments, particularly the Australia telescope. None of it happened. The purposes for which these instruments were built rarely produced any major discoveries. In fact, they rarely got, the projects rarely got done. But the capabilities that these new instruments had led to fantastic science and many, many new discoveries. In other words, you could say, bugger the bill, just pay it. The astronomers, the scientists will make new discoveries with new tools. But of course, the final thing is to really understand how we make scientific discoveries, we've got to understand the scientists. Scientists are human beings. They're the Homo sapiens that actually do that science. There are 2 sorts, really, I've learned. There is a specialist expert. He knows a lot, but in a relatively small range. There's also the generalist expert that knows a little bit about each. Each of them have their strengths. It's good to know a heck of a lot about a topic, but you sometimes learn faster and make more discoveries by having a broader level of knowledge. See, scientists, you'll read or everywhere, think they use the scientific method. That's a load of rubbish. We have in the back of our mind the myth of the totally objective scientist who's always a little bit mad or effeminate, for example, if she's a woman. They're supposed to follow the scientific method. They observe and then they carefully analyze and produce a theory. They go on to test that theory and then they modify it slightly and they observe again and so on. That's a load of rubbish. It's never happened in my lifetime. There's a lot more fiddling, confusion, and everything goes on. We are human beings. We're not these impersonal, white-coated people. That's a diagram of a scientific method. It's not mine. It comes from New Scientist magazine. I could, in the recording is probably the time to have a look at that in a little bit more detail. But as you can see, there's a whole load of human activities built in there amongst the science getting done. And that is much closer, in fact, to the real way it's done. Perhaps if there was a scientific secret, I would say the most powerful tool we have is being able to say, oh, I was wrong. That didn't work. I messed it up. Let's try again. You see, real scientists are after the truth. Real scientists after the truth. And scientific truth is how the universe behaves, not just what we think it's going to do or how we want it to be. And all truth is not the same. There are people in this world, possibly in the United States, for example, who say in our everyday world, if you say it loud enough or often enough, then that was going to make it true. You may have a person in mind who does that rather well. I couldn't possibly comment on that. However, all truth is not the same. In particular, what the media popularize is generally nothing to do with true things, but new things. They give us a distorted view of science. The number of times I've been asked with a microphone on my nose, what were your major breakthroughs today? It doesn't work that way. It doesn't even work if I were to change that to this year. It takes a lot of perseverance and, as we've seen, hard work. A thing to realize too is, I often describe it this way, and these are just my words. There's what I call Monday to Thursday science, the big block of the week's work. Monday to Thursday science is the science that in fact is well established. It's beyond doubt, almost. It's very unlikely to need any more discoveries. It's such things as the energy source of the stars. We think we already know pretty damn well what's going on there. Then there is most of Friday science. This is the more exciting stuff. For example, dark matter fits in there very nicely. It is attainable. It's attainable by the scientific approaches. We don't know all the answers, but it's interesting stuff. But there's a lot of speculation. No doubt a lot of this could well be wrong. Finally, there's what I call the last hour of the week science, and that is the highly speculative stuff, such as entangled particles, how they can possibly interact. Parallel universes fits in there. The interesting thing is when you go to the media regard all of this as totally boring. They would never, ever put articles out on this. On the other hand, most of Friday science, well, yeah, that gets a fair bit of stuff, but they just love the last hour of the week science. They always are coming back there and saying, what is this? What is parallel universes and so on. So they distort it. You see, our universe is a pretty hard place to try and understand, but it's only understandable if we're after the truth, not just the opinions, not the news value, not the personal status of ourselves. And so there's one final thing we've learned. As I said before, we need investigators with honesty, curiosity, who are not scared to say, I was wrong, let's have another go. You see, we've come a long way in the last 2,000 years in getting to know our unknown universe as it was. And I'm sure we're going to make a lot more discoveries, incredible discoveries in the next 2,000 years. And that's just as well, because we've only just begun to learn about it. We humans, we haven't been in this universe long, as I said, Homo sapiens. And of course, we've got to provide job security for our young astronomers. Thank you, ladies and gentlemen.
Thanks, Alan. Do you want to go back to sharing, please?
Unsharing.
Unsharing, yeah.
Yep, there we go.
Great, excellent. Well, that was fascinating. I have to say I preferred your first bit. I like to, I think you could expand on that hugely. That could be about 27 hours, I reckon.
Absolutely. Which bit were you talking about? The first section of the whole?
The first part before the break, yeah, the whole history stuff. It's just
the actual detail of that I had covered in the to some extent in the Lifting the Lid series, of course.
Yes,
with different topics. But I mean, there are so many more things to do. Yeah.
Mm. Anybody else with a comment or a question?
I'd just like to say thank you, Alan. That was absolutely brilliant. I could listen to your voice all day.
Terrific. You're welcome.
And I did ask if you ever do podcasts.
No, I don't. No.
Well, I reckon you could.
I'm sure you could do a lot of things. It's it's a big universe, and there's a lot of time in it, and there's a lot of things to do. But yeah, maybe this is the time to look into that. I don't know much about it. I use social media, but I don't necessarily do it too much. But yeah.
Well, thank you very much. That was fantastic.
Thank you.
Yes, thank you, Alan. Really enjoyed that.
Yeah.
Okay, so
I really enjoyed your second part, or the last part, the philosophical questions.
Good.
I'm really interested in that, and I like it. Well, somebody famous once said, the more we know, the more we, or if we think we know everything, we know also that we know nothing.
That's right. Well, it said, you know, if I have seen further than others, it's because I've stood on the shoulders of giants. And that was not modesty. That's exactly right. That's the way every, you know, successful scientist would actually say. They are standing on the shoulders of those that have gone before, rather than starting again.
I also like your diagram of how science works. And everything. I think that is just so true, not only in astronomy, in many things.
No, that's
on a practical note, Alan, for the subject matter is beyond my old tired brain, really. It's fascinating, but yes, I'm probably much too old to learn what I need to know. But what's so good about your presentations from a lifelong learning point of view is your use of analogy and your diagrams and the photographs or the slides that you've used to help make something that's enormously difficult for some people into something that is
Thank you, Jo.
able to be understood.
Exactly.
Thank you, Jo. I appreciate that.
Yeah.
Commercial, and that book, which I'm sure you can see in the recording if you really want to, or you can just email me. I'm very happy if anyone wants to email me, Reese, and I'll give you the title of the book and so on. I think, Hilary, you actually had looked for that, and it's not easily available, is it?
No, Alan, I have an alternative idea. I had a moment to think that while I made the coffee, and that was what a wonderful topic for U3A next year for Alan to talk about the women in astronomy and their achievements. And so rather than us looking up, we might leave it to you to give a presentation.
Yeah, I'm a bit of a traditionalist, because I believe that women are totally equal in it.
Oh, hooray.
So to give, I think to give a talk just about women in astronomy could be sexist. No, it's a possibility. Yeah, it's a good possibility.
Yes, good.